Welcome to your first lesson in second year IB. In the very first short unit, we will review a lot of things that you have learned in your grade 11 pre-IB course, including exponent laws and logarithm. Okay, so for today's lesson, we will be reviewing exponent laws and by doing examples and also solving exponential equations. You may also wish to pause the video now and try the questions before you check the solutions. So here we go. Simplify 49n to the power of n minus 3 over 14 to the power of n minus 3. So we notice how 49 and 14 share something in common, but according to order of operation, we cannot just reduce 49 and 14 right away by the way they're written in the question. Therefore, we can use one little trick, which is to note that since both 49 and 14 share the same exponents, we can write the power in this form. And now this allows us to simplify 49 over 14 as 7 over 2 to the power of n minus 3. You can leave your answer like that. This is just rewriting or simplifying this particular expression. Question B. We see a couple of friends here. We have a rational exponent, 2/3, in the numerator with a base of 8p, and a negative exponent, -2, in the denominator. My habit to simplify exponent or like powers would be to get rid of all the negative exponents as soon as I can, unless there's an easier way to simplify the expression. Okay, but most of the time, I don't like the distraction of that negative exponent. So in this case, I can rewrite 8p to the power of 2/3 and multiply by 4p to the power of positive 2. Okay, so then I will worry about simplifying, expanding the brackets now. So note that how we have an exponent of 2/3, which really means that take the cube root of 8p and then square the entire thing. So it's easier to think of this way. I'm going to write it out, but you don't have to do it this way if you're familiar with the rule. Right, for the numbers, I usually write it in the root notation or in the nth root notation. For variables, I will just use the original exponent, because then I know I'm multiplying this by 4 squared, 16, times p squared. So simplifying cube root of 8 is 2, squared that is 4 times 16. In terms of the exponents of p, because I'm multiplying p powers of p, I'm going to add their exponents. And finally, this is 64, p to the power of 3 times 2, 6 over 3, 8 over 3. Okay, if you're comfortable with simplifying this expression, you may have skipped a couple of lines, and that's absolutely okay. Question C. So take a look at the expressions. Oh, once again, I see a negative exponent. So very naturally, I'm going to take the reciprocal of 9v squared over 16w to the power of 4. Another thing that I should make a decision on would be the power of 1/2. Should I write it as a square root symbol, or should I leave it as 1/2? It's really your personal taste, I would say. In this case, to me, I prefer to write that as a square root. So let's do that. And then if you like, we can start expanding the second power. So the cube of 3 is 27. V squared to the power of 3 is V6. W to the power of 3 cubed is W to the power of 9. Okay. Simplifying further, square root of 16, 4. Square root of W4 squared. 3V here times 27 V6 W to the power of 9. So I noticed that, 3 and 27 can be reduced. And then V and V6, this is V to the power of 5, and then I can multiply out the powers of W. As a result, I get 36 TUV/W. So V goes first, and then W to the power of 11. Okay. Last question on the page. We've got this. Very interesting setup, because the square root of 8x to the power of -3 doesn't really simplify nicely. So I'm going to stick to my own rule again. Numbers, I use the root notation, and then for variables, I use the rational expression, like rational exponent, okay? So let's rewrite this thing. And then for the y to the power of -2, because my preference is to keep positive exponents as much as I can, I'm going to write y squared in the denominator instead. The square root of 8, I'm going to write that as 2√2. So I'm going to simplify that. And then here I have x to the power of -3 halves, right? Because that's the square root. I could have written that as x to the power of 3/2 positive in the numerator. Okay, so let's simplify. So 6 and 2 can be reduced. If you're picky, here we go. We can rationalize the denominator at the same time. And so we have 3√2 x to the power of 7/2 when you add 2 and 3 halves together. And then in the denominator, √2 times √2 is 2, y squared. And that's your answer. So in the next video segment, we will move on to page 2. Okay, on page 2. Now we're going to solve a bunch of exponential equations. The key to solving exponential equations is to remember that for the most of the time, you're really thinking about comparing the base of the left side and right side of the equation, so that you can just drop the base and then compare exponents. Okay, compare powers of the same base. Let me write this down. So that would be the key, okay? Especially when you don't have a calculator, you basically have to resort to this particular method. All right, so let's take a look. I have a power of 4, a power of 8 on the left and right side of 2a. I can't write 8 as a power of 4, but both of these can be written as powers of 2. So let's start with that. Using exponent laws, power of a power, I multiply the exponents. Okay. So now I have powers of 2 on both the left side and right side of the equation. Let's compare the exponents and solve. So 6x minus 2x is 4x. 2 plus 12 is 14. Therefore, x is 7/2. Good. Question B. So good news is we have powers of 2 on both sides of the equation already. So we can easily just compare x squared minus x equals to 6. This really is a quadratic equation. So now what do? We have to swing the 6 to the side so that we can make the right side 0. I can factor x squared minus x minus 6. I need -1, so it's -3 plus 2 here. As a result, x is equal to 3, or x is equal to -2. So if this has helped you to refresh your memory, you may want to pause this video again. Try the next couple of questions in your notes before you come back to review the answer and check your solutions. And once again, a lot of these questions that involve exponent laws or exponential equations may have different ways of solving it. So even if your solution is different from mine, doesn't mean that you have done something wrong, okay? But just make sure you have followed all the rules of algebra and math very carefully, okay? So hopefully you have actually tried the next few questions on your own before coming back to the video. So let's check your solutions against how I do it. So in this question, I know that 3 is kind of like extra on the left side. So I'm going to divide both sides of the equation by 3. This actually makes it better because now I can write the right side as 9 to the power of negative 1 compared to 9 to the power of x minus 5. Therefore, x minus 5 is negative 1. X is negative 1 plus 5, so 4. Question D. 343. We don't really see this number a lot, but looking at the equation on the right, you have square root of 7. So check the powers of 7. It turns out 343 is 7. Oops. To the power of 3. And the right side, I can write it as 7 to the power of 1/2. As a result, I know that 15x must equal to 12. Divide both sides by 15. X is 1 over 30. Question E. This is a little more messy than the other parts of this example. While like solving a lot of equations, we usually gather terms that involve x's on the same side. So why don't we try that first? So 54 is 3x. Well, 3x plus 1. If you reverse the addition in the exponent, it really alludes to 3 to the power of x multiplied by 3 to the power of 1. And then we're going to subtract 3 to the power of x from the left side, which means I can factor 3 to the power of x and have 3 minus 1. This is good because 3 minus 1 is 2. Divide both sides of the equation by 2. I get 27 equals to 3 to the power of x, and knowing 27 is 3 cubed, x must be 3. So this is the second example in the lesson. When you're ready, let's move to the next page. So the reason why we're learning how to solve exponential equations is that it has a lot of important uses in like science and also in finance. You may already be familiar with its application in solving half-life problems on radioactive substances and also compound interest. So let's take a look at how we can do this, or as a review, that works too. So remember that half-life means that it's the time it takes for radioactive substance to decay into half its activity. The activity is halved. So given this situation here, you may also recall that the amount of activity remains, so sometimes in math we just refer to the amount left, is based on taking your original amount A0, and then every time it undergoes one half-life period, you only get half of the original amount. So you'll keep multiplying by 1/2. But how do we keep track of how long or how many half-lives has passed? Well, then you take the actual time t, and out of the half-life of the radioactive substance, here I'm just going to call it H, okay? So this is like a standard equation. So back to the question. So we're given that strontium-90 is used in machines that control the thickness of paper during the manufacturing process. Strontium-90 has a half-life of 28 years. So like science questions, you may wish to write down your givens on the side. And then determine how much time has elapsed if only 1/32 of a strontium-90 sample remains. So you're really given the end result, right? 1/32 parts of the original remains. So now by writing it in this form, we don't really care how much A naught is. And we are looking for time, T. So let's substitute these numbers into the equation of the formula. So 1/32 A naught equals A naught times a half time over 28. We know that A naught will cancel out, and 1/32 is a power of 1/2, so that's convenient. I can write the left side of the equation as 1/2 to the power of 5. And then 1/2 to the power of T over 28. As a result, all I have to do is really to compare these exponents and make T equal 5 times 28 or 140. Okay, so you can say that it takes 140 years for the sample to reach 1/32 of its original amount. Okay, so let's move on to example 4. This is a compound interest question. First, we're going to solve it by hand, and then we're going to add on a part where you can use an app on your calculator on the TI-84 called the TVM solver to figure out the answer to this question without having to remember the formula. So you deposited $9,200 into an account with an interest rate of 4% per annum, compounded quarterly. How many quarters will it take for your account to reach a balance of $15,000? All right. You may recall, once again, a formula to do this. The amount of money that remains in your account is equal to the principal, P, multiplied by 1 plus, okay, some people use I, some people use R. Well, when I'm compounding quarterly, every year you compound it 4 times, right? So you have to divide your annual interest rate, I'm just going to call it I, by 4. And then the number in each year, you're going to have 4 quarters. So basically 4T, okay? So given this formula, the amount that you want to reach is $15,000. Principal is $9,200. 1 plus your annual interest rate, 0.04. But each quarter, you're really gaining 1%. And then how many quarters does it take? Well, T is in years. So instead of writing T, I'm just going to call N. N would be the number of quarters that we need. Now, this is a little tricky because we can't really solve this particular equation using our standard powers, right? Because you have 1.01 to the power of n. But I don't know. It's complicated, right? Powers of decimals. Can't do that. So you're going to reach ahead a little bit. We're going to talk more about log tomorrow. And take out what you know about log and say, well, but if I log both sides of the equation, that will allow me to bring n to the front, remember, as a coefficient, so that, in other words, n really is log of 15,000 over, so I'm going to cancel out the zeros first. I don't really care. Okay, so I'm going to plug this into the calculator after. Like that, right? And then this works out to 49.12 ... So that means it will take 49 quarters and slightly bit for the account to reach a balance of $15,000. Okay. Or you can just say 49 quarters. There we go. So this is solving the question manually. When you take out your TVM solver or your graphing calculator, you're going to notice that you can actually follow apps, go to Finance menu, and go to the TVM solver menu. And then there'll be a big chart showing different letters, N, I, P, V, PMT, all these good things. And on this slide here, I have actually included the meaning of each of those numbers. A few more things to note is that number of compounding periods here is based on years. And then when you're depositing something, you are giving away money, right? It's just thought that, well, the money's leaving you. So when you put down the present value part, this is a negative value that you have to enter because you're giving away. When you deposit. Okay. And then future value in this case would represent how much money you want to have at the end of your investment. And then the number of interest compounding periods per year that you have, because this is quarterly, you will be using 4. So let's write this down. Annual interest rate is 4. Present value is negative 9,200. Future value, 15,000. And then number of interest compounding periods per year, it's 4 for quarters. Okay. And then because you're looking for N, you're going to move your cursor to this field and then press alpha enter. That should give you the same answer as what you have calculated by hand. Now notice how you will get a different number for a reason. Remember we said N is by years. So if you get an answer of 12.28 years when you do this, you have to multiply that number by 4 to match up with how many quarters in total you'll get out of that 12.28 years. Okay. I will make a separate video to show you the screen of what it actually looks like on your calculator. Okay. So first you have to locate apps, and then we're going to look for finance 1, and then we go to TVM solver 1. So it brings you to the screen with the menu. So remember, number of compounding periods are calculated in years based on what we're going to enter. We're going to go down to I for interest, 4%. PV is what you deposit, the present value. So we're depositing, money's leaving you. This is negative 9,200. We skip the PMT part because it doesn't apply in this question. It's okay to leave it at 0. Future value is 15,000. Now you're bringing this money back to yourself. So this is positive. Well, we're going to try to keep payments per year, P/Y, as 1 first. Okay, we're going to compare the results. And then number of interest compounding periods per year. This is quarters, so 4. All right. Payments are made at the end of each period. So now we have entered all the givens. Move your cursor to your unknown. In this case will be how many compounding periods. And then to solve, we press alpha. enter, because look at the green letters above the enter button is solve. And here we go, 12.26 years. Now I'm going to try something different and see if it works. Go to payments per year. So instead of making one payment per year, because it's kind of like the whole year, how much do you get? What if I change it to 4 payments per year to kind of match up the compounding cycles? Now I go back to N. I press alpha solve again. Guess what? It does give us 49.12 quarters. That matches the answer that you have calculated by hand. Okay, so either way works.